So I think it's the last problem that we need to cover out of the chapter. I'm going to try working a lot of this on the screen. So let me sort of set up the problem for you. We had done some calculations with a bomb calorimeter. You guys remember what a bomb calorimeter is, right? It's that you can imagine it as a big fancy coffee cup with a steel container on the inside. And we do the combustion inside the bomb calorimeter. And then we measure the temperature change, and then from that we can figure out what the enthalpy of a reaction is. So let me write the numbers up here and draw a picture of what's going on. So here's your bomb calorimeter. It's drawn as a big blob like this, and there's a box on the inside. And then inside this particular calorimeter, we have C10H8, which is naphthalene. And then we have, the little fuse that comes out. And there's a liquid in here. And then we also put in O2. And then we ignite it, right? We push the little button and go psh. And when it burns, what happens to the temperature on the inside? It goes up, right? So it says it goes up by 5.92 degrees. So that's actually the change in temperature. When it says it increases by, sometimes they give you a final temperature and an initial temperature. If they do that, you just subtract the two, and then you get your change in temperature. Now, the other information they give you in this problem is they say that the heat of combustion is equal to minus 5,153.5 kilojoules. So normally, like when we do these problems, what we're trying to figure out was actually trying to figure out this number, okay? But instead, what you do in this problem, what it's asking you to do is figure out what the heat capacity of the bomb calorimeter is. So this is kind of like figuring out what the calorimeter constant is, like you did in the last experiment where you run a reaction and then you figure out how much heat is lost. So what we're actually doing in this experiment is we're setting it up so that the Q of the calorimeter plus the Q of the reaction, conservation of energy says that that's equal to 0. We're setting it up so that we know the amount of energy that comes from the reaction from the heat of combustion. That's how much energy comes up when you burn it. And we're going to figure out what the energy absorbed by the calorimeter is. Okay, so let me set it up on the screen real quick. Okay, so I know that Q cal plus Q of reaction or combustion equals 0. Oh yeah, forgot one thing, hang on. I have 1.108 grams of this naphthalene. Okay, so 1.108. I'm going to figure out what this is now. So I have 1.108 of C10H8 and what I need to do is I need to convert that into the energy that represents, okay? So when I say heat of combustion is minus 5,153.5 kilojoules, that's the amount of energy produced for 1 mole of C10H8. And it's actually for the reaction of C10H8 plus O2 goes to, and then CO2 and water. So heat of combustion is kind of like a jargon term that they use in chemistry. It's how much energy you get when you burn it, but it's by default for every mole of whatever that substance is, okay? So if that's the amount of energy it takes per mole, and I have the number of grams, all I need to do is take the grams, figure out what the molar mass is, convert that to moles, and then use this energy to figure out how much heat is released by the reaction. So I'm going to ballpark some of these numbers. Intentionally choose things that have meaning or are easy to calculate. So C10, all right, and then H8, it's 12.01 times 10. That's equal to 120.1 AMUs, and then H8, right? It's 1.008. I'm going to ballpark that as 1.01 times 8. So that's 8.08. So it's 128.18 atomic mass units. Make sense? Right? Just calculating molar mass. So now I can go 1.10 grams, 108 grams. And 128.18 atomic mass units. That still has 4 sig figs in it for every 1 mole. And then 5,153.5 kilojoules per mole. Okay, and the only thing I'm missing is the negative sign. A lot of times people do the calculations, they just leave it out, and they know it's exothermic. They kind of know. But I'm going to put it in because we need it for our calculations, okay? Okay, so I do my fancy math. Oh, Microsoft is trying to update something, sorry. Stop it. And that gives me negative 44.54 kilojoules. So that's the amount of energy that's released, and that's this part here. Okay, so what's Q for the calorimeter then? How much energy did the calorimeter absorb? Yeah, just the opposite of there, because the only things... If there had been some other thing going on in there, then you wouldn't be able to say that. But since it's the only 2 things, we know Q of the calorimeter is the opposite, so it's 44.549. And then you guys remember when you do a calorimeter constant, it doesn't have units of mass in it. Yeah. Oh, yeah, yeah. I have not done the I'll round it at the end and track it all. So that's equal to C delta T, not MC delta T. And then all I need to do is recognize that it gave me the change in temperature. It's 5.92 degrees, and so the calorimeter constant is just a 44.549 divided by the 5.92 degrees. That comes out to be 52527. And that's in kilojoules per degree Celsius, and then 4 sig figs. I'm actually going to use this number in another problem, so I'll round it like at the very end. Okay, so why would you do something like this, right? Remember I talked about like an M&M and how much energy is in an M&M? The way they know how much energy is in an M&M is they burn it in a bomb calorimeter. But before you actually can calculate how much energy is produced by the burning of the M&M, you have to calibrate the instrument. And so the determining of the heat capacity of a calorimeter is actually the first thing that's done before you actually stick a sample in and you burn it to figure out how much energy it releases. So they know how much energy naphthalene produces when they burn it. It's a sort of a standard reference compound. They'll put that in the bomb calorimeter. They'll burn it. They'll get a number, the temperature change, and then they'll take those numbers, calculate the calorimeter constant, and then throw in whatever sample it is they're trying to analyze, like a peanut or an M&M or a piece of fat or flour or sugar or those kinds of different things. Go in the calorimeter, and they measure the energy that's produced. Any questions real quick? We'll go on. So here's the rest of the problem. It says if the combustion of 1.315 grams of thymol, which you don't really care that it's thymol other than you need the formula, okay? If the combustion of 1.35 grams of thymol causes a 6.74 degree increase in temperature, what is the enthalpy per mole of thymol? How much heat is released per mole of thymol? So I have 1.315 grams of, and this is the important part, C10H14O, and there's a change in temperature, so delta T is 6.74 degrees Celsius. We want to calculate Q of the reaction, that's the enthalpy for every mole for thymol. And then we're also going to write out the thermochemical equation, so C10H14O plus O2. We'll finish that when we get there, okay? The calorimeter constant, by the way, is still, in the previous part of the problem, 7.52527, 4 sig figs, kilojoules per degree Celsius. Okay, so again, we're going to base everything on the premise that the Q for the reaction plus Q for the calorimeter equals 0. All right, and we have all the data to figure out how much heat is produced by the calorimeter now, because we have the heat capacity or specific heat. If you want to call it that, it's really heat capacity of the calorimeter. What else do we have? Change in temperature, right? So in order to get the energy that's produced by the reaction, I just need to use Q is equal to C delta T and that's going to be 7.52527 kilojoules per degree Celsius times change in temperature, 6.74 degrees. So those degrees Celsius will cancel. And then I end up getting 50.72 kilojoules. Three sig figs, because temperatures are often, like it is in this case, what limits your significant figures. And what did we want to calculate? We wanted to calculate from that the number of heat, the amount of heat per mole. So what's the only step that's left for that calculation? What's that? What? Yeah, just convert it to moles. And then you take that energy and divide by the number of moles. So I have 1.315 I think everybody's getting on the internet now, so now the connection slows down, and as I write, every once in a while it just stops recording. You'll just see this big line go across. You're like, ugh. So I have to erase. Okay, grams. And I want to convert to moles, and then to save us all a little bit of time, the molar mass is 150. And then I don't know why I have so many sig figs on that number, but 150.22. I'll put 1, but I actually have more than that, grams for every 1 mole. So you have 0.008 75380 moles. So then to get the enthalpy per mole, the Q per mole, that's 50.72 kilojoules divided by the moles, which is the 0.0087538. A lot of skipping going on here. And then that comes out to be this gigantic number, but heats of combustion are often very large. 5,790. That's kilojoules per mole. Okay. So that takes care of all the calculation part of it. The rest of it is just write the thermochemical equation. Okay. Oh, what am I missing? Negative sign. Thanks. Why is there a negative sign there? Yeah, Q of the reaction is the opposite of the calorimeter, right? Just from that first line that I wrote, I got to the end and I realized it's a combustion reaction, but it's positive, so that can't be right. So then I looked back to see where the mistake was. All right, so the last part is to write the thermochemical equations. Let me write this on the board really quick. Minus 5,790 kJ per mole. Okay. So I have that number. And then what I'm going to do is I'm going to go ahead and balance the equation really quick. So I know that thymol is C10. Hang on, guys. I got to pause for just a second. Okay, so C10, H14O. That's a solid, plus O2 gas makes CO2 gas plus H2O liquid. And so I need to balance this. I should have probably left a little bit more room in there, huh? I'm going to cheat. Just going to move stuff around rather than rewrite. There you go. Yeah, left more room in there. How do I balance? Ten CO2s. 13 O2s. Oh, you're way ahead of us. And 7?
Yeah,
7 H2O, yeah. So that's the balancing. Okay, so you notice something here, though. This is kilojoules per mole, and in the thermochemical equation, it's written for how many, that equation right there has 1 mole of the thymol in it, right? So the way you have to think about this heat of combustion is I have 1 mole of C10H14O and times 5,000 negative 790 kilojoules for every 1 mole. That'll cancel out. And so that ends up being 5,790, right? And these energies that are over here on the thermochemical equation don't have per mole written in them because they're written for the way that the equation is balanced, like it is here. It says a 1 in here. You know how sometimes when you do combustion reactions, you end up having to double the reaction, right? And you end up with like a 2 in front of whatever the hydrocarbon is, or a 2. Hello, right? You know what I'm talking about? Yeah. So if that's the case, what do you have to do down here when that happens? You have to double it, right? So if this had balanced out, and this had been a 2 over here, then this would have been more like 10,000. Something, or 11,014, okay? 11,400, yeah, there we go. I think that's right. Huh? Yeah, so you have to multiply by the number of moles of whatever it is in the reaction, okay? Well, that's just a note to be careful of. Okay, any questions about the homework? Everybody told you, hey, take a look at the homework. We can talk about the problems. Everything go okay in the homework? Procrastinator? It's okay. People still get it done. It takes it looks like it's taking people about an hour and a half to get the homework done. 2 hours. So you got plenty of time. Take a nap, go home. Yeah, or go home, take a nap. Don't just take a nap and then go home and be like, where am I? That would be like my life. All right. So no questions on it? There's one problem I thought maybe people would ask questions about, so let me go ahead and put it on here. Okay. So I'm just going to do it in a sort of generic terms, okay? So I'm going to do it with A, B's, and C's, and I'll make up random coefficients and stuff, okay? Just so you can see the concept. So let's say you have this reaction of A plus 2B makes, I don't know, C. And then they tell you that the delta H of the reaction is a number, right? So they give you the number. So let's say it's 1,000, just randomly make up a number. and kilojoules. And then if you were normally going to calculate that number, how would you do it? You would do products, right? You calculate the product energy. This is what we did in the last lecture. So you would look up, you would balance, you would look up the delta H's of formation, and then you would calculate the delta H of the products, and then the delta H of the products and the reactants, and then you would do delta H of the reaction equals, and then it's the delta H of the products minus the delta H of the reactants. Right? So that's like the normal process. But let's say you don't have A, and that's the actually you want the heat of formation for A. You can actually have like B and C, right? Then measure the energy produced by the reaction, like in a calorimeter. So you can have this one, but have this one be unknown. Okay, so how do you solve for this one? Well, if you have this energy and you have the energies of formations for B and C, this is the only unknown that you have left. So you can solve for this one. So you do this whole calculation, right? Just like you go all the way down to here and just leave this value as an unknown x. So this will be x, and then down here, this is equal to the quote-unquote 1,000 kilojoules. And you can solve for the one that's left to calculate, okay? So that's how a lot of these are determined, right? We know a lot of enthalpies of formation for lots of compounds. You get a new compound, you put it in a reaction, and it's the only unknown you have because you measure the energy from the reaction.
Can't you do, like, if you have 1,000 and you have that one subtracted and you get the A?
Well, you have to have these values before you can do that, right? So you. Yeah, that's what I'm saying. So you look them up. Yeah, so that's exactly what it is. You take this minus this, right? That's this minus these. And that's just equal to that. And so you just have to do that. You have to do the algebra and solve for it.
Okay.
Yeah. Okay, so if you get stuck, feel free, people do, they post questions on Canvas. Feel free to post a question on Canvas. I'm up till all kinds of crazy hours. Normally I'm up working. Now I just can't sleep. So it's like awesome, horrible combination of I'm tired, but anyways. So I drink coffee. That's only my first cup of the day, by the way. What's that? Yeah. I can't sleep because my sleep cycle's all thrown off. Then my wife says, why don't you just take some melatonin at night? I'm like, great, and then I won't wake up in the morning. So, I mean, that might be good for you guys, but then you... Okay. So this is what you kind of saw, right? So what are you looking at here? All right. What's rainbow, right? This is, let me make the pen a little fatter. So this is a rainbow. Let me go on the left-hand side. Yeah, we'll go from here. So that's our rainbow, right? And this is red on this end, and there's orange in here, and yellow. So that's Roy. It spells Roy, right? And then green. And in between there's kind of like a teal color, right? And the camera doesn't do a very good job, but there's indigo. And there's violet. And it's probably because the light source doesn't really have it in there. But if you actually were to look outside and like look at filters, don't look at the, they always say you don't look at the sun. But if you were to look at the filtered sunlight, you would see more of the rainbow. So these are exactly the same colors. Sorry, I missed the blue in here, huh? This is the blue. These are exactly the colors you see in the rainbow, so Roy G. Biv. That's what we abbreviate it as. Have you ever seen a color wheel? A color wheel? Color wheel takes these same colors and puts them in a circular pattern. All right, and the colors, they're roughly evenly spaced, red, orange, right? Yellow, green, blue, indigo, violet. You ever heard the term of like complementary colors, right? Complementary colors, right, if I remember right, are on opposite sides of the color wheel. Yeah, right? So here's the thing, that the reason that complementary colors are important. Oops, I didn't space it correctly. Something like that, right? Is if you block out these colors, right, you're going to see these colors over here. So like you take white light and you filter out certain colors, and what you see are the colors that are left, okay? So the reason that's important, like you look at this paper, it's white, right? So it's reflecting all the colors of light. On the other hand, when I hold up that, right, it's let's call it blue. Okay, that's kind of what you're seeing here, because what's happening is light is coming down and reflecting off that piece of plastic. It's absorbing all of the colors complementary to blue, and then you're seeing the blue being reflected off the surface. Okay, so what's happening to the colors? Why are they not all reflecting off? What do we say? They're absorbed. Yeah, they're absorbed by whatever the material is. And so here's the question. Why is it absorbing those colors? Right? And this is the kind of question we're going to try to answer by the time we're at the end of this chapter. But this chapter, the title, anybody actually know what the title for the chapter is? It's called Electrons and Atoms. It's kind of this really vague, like, sure, there's electrons and atoms, right? So, title is Electron and Atoms. Which one of those looks like an atom to you? The blue one, right? Why? Huh? It's bigger, okay. Any other reasons why it looks like an atom to you? It's a sphere, because your whole life you've been told, right? Atoms? Well, there's these little solid sphere-like things, right? Why do we do that? Because we have no real idea, at least, what they look like, at least at this point. Turns out these are all representations of atoms. In fact, what they really are, if you think about what an atom is, the nucleus is this little tiny thing. What we conceive as being an atom are actually the electrons that are circling the nucleus. And that's what gives the atom its shape. And so we kind of think nebulously that the electrons sort of go around a sphere like this. But in fact, very few of the electrons in an atom get to occupy a space that's spherical. The space that's actually occupied looks, in large part, like these guys do. It's space. If the nucleus was the point, this is X, Y, and Z. If the nucleus is a point in the middle, right, the rest of the space occupied by electrons is divided up in spaces that look like this. Okay, so what we're going to try to understand is why they occupy spaces like that. And this is just another representation of some of these diagrams. So we'll get to those at the end. But really, all of these are what an atom looks like. Okay? It just depends on what aspect that we're trying to see about the atom. Oh, I'll come back to this slide on the next lecture, which is some review stuff. Okay, so we've got to understand a little bit, in order to understand the behavior of electrons, right? Turns out the reason this paper sorter is quote-unquote blue. It's teal, right? But the reason it's the color that it is because it's absorbing light. The reason it's absorbing light is because the electrons are capturing that energy, and then actually dissipates it usually as heat. Okay? So the electrons are capturing the energy, dissipating it as heat for the colors that are complementary to what you're seeing here. That make sense? So now we're going to try to understand a little bit more about electrons, but in order to understand about electrons, we actually have to understand a little bit about light. Okay? So there's a guy named Michael Faraday, very famous. I say he's a chemist. Physicists probably say he's a physicist, but that's okay. Because they're famous, really well-known people. We just try to claim them as our own. But he was a natural philosopher in a lot of ways. That means he studied everything. He took a piece of metal, an iron, like horseshoe ring. That's what this is. Okay. And wow, that's weird. Going really slow. He wrapped it in wire. Okay. So what you're seeing on here is wire wrapped around a big iron ring. And I was telling the other class before, he didn't just go to the store and buy this. He had to make a lot of this stuff. Right? Didn't have like a plug he could plug into. He couldn't go to the scrap metal shop. He had to go to a foundry or make a foundry, make stuff himself. He had to draw the wire himself. He had to wrap the wire himself. So this is like not like, oh, let me do this project. Like we're all doing these projects at home, like these gee whiz do-it-yourself projects. You see them on YouTube, and you go and you buy stuff at Home Depot, and you put it together. It's not exactly how he did it. Okay. So to be really like clear on how hard some of this stuff was to do, you need a battery to do this experiment. Okay. So you would take a battery and plug one end of the battery here, and on a switch, have the other end connected here, and then you flip a switch. And he was passing light through this piece of glass that he made. And you take sand and you melt it down. Glass, it's one of his big projects. He spent many, many years trying to make glass. Okay? Passed light through this piece of glass, and when he turned, he like closed the connection to the battery, right? The light turned. So here's the thing you got to understand. When you do this, this is like one of the early electromagnets. If you take a piece of metal and you wrap a wire around it and you run an electric current through it, it magnetizes the piece of metal. And what he was able to show is that when you magnetize a piece of metal strongly enough, the light around it curves, or the light that goes through the glass curves. Okay? Okay. You know who he got his first battery from? Okay, get this. Volta. Why is that a name associated with batteries? Because he's like one of the first battery makers, right? Volta and Galvani made batteries. They used them to torture frog muscles and things and to watch them twitch, right? Well, that's, anyways, yeah, sorry. That's why they were so fascinated by electricity, because they figured it had something to do with life, because you could take a muscle and touch it with the leads of a battery, and the muscle would twitch. So yeah, Volta, the guy who made the battery, who we named the Volt after, gave Michael Faraday, when he was in his old age, gave Michael Faraday a battery so that they could go and study it back in Europe, or in England, I should say, because Volta is Italian, so he was in Italy. Rome, I think they met in Rome or something like that. Yeah, so like it needs a battery, but like if you have to go to Volta to get your battery, you know this is not an easy task, right? It's not an easy task. So he says in his notebook, I've at last succeeded in magnetizing a ray of light. Okay, so here's the thing. Let's say this packing peanut is traveling through space, and let's say it has a charge on it, right? And then it runs into an electric field. This is the way it's easiest to understand. Going through an electric field. What will this thing do when it gets to the electric field? Will it continue to travel straight? So this thing has an electric field as well, and as it travels through space, the electric field of the particle interacts with the electric field around it, and it moves, okay? If light moves in response to a magnetic field, what does it tell you? What? It's made of particles, but, I mean, you can't make that conclusion. Yeah, it's true, it's made of particles. We call photons, right? But it tells us that light has a magnetic component to it. So light, so when I say, we talk about light and we treat it as a wave, right? When I say, oh, water, there's waves in the water, what's waving? Like you're in the beach, right? Waves are coming at you. What's waving?
The surface of the water.
The surface of the water, right? There's a medium that you can see. This is why we like water waves. There's a medium that you can see, and it moves up and down, and what's waving in the wave is the water. It's going up and down, and as it goes up and down, these waves travel. You can actually watch waves move across the water, right? So when we say light wave waves, right, there's light is made of waves. It has all the properties of waves. We'll talk about that. The question is, what's waving? What's going up and down? What's the medium through which light travels? Like water, right, waves travel through water. Sound waves, what do they travel through? Air. It's the compression and decompression of the air as the air, sound waves move along. So light waves do the same thing, and it turns out the thing that Faraday is trying to figure out here is like, what is waving when light is traveling, right? And it turns out, I think the settings on this are messed up. Hang on, let me do something real quick. Oh, disable auto lock is on. I don't know why it keeps wanting to lock up on me. Sorry. Okay. Light is what we call an electromagnetic. I have to write it sideways. Electromagnetic wave, and it travels, right, through an electromagnetic field. Now, you don't know that that electromagnetic field is around you, right? But this is like the evidence that light is an electromagnetic wave because you can affect it with a magnetic field. So it must be traveling through an electromagnetic field. Right? We don't think about the electromagnetic field, but it's there, okay? You also know if light is traveling, okay, now I'm talking about in general terms of light, but let's say here's a light wave, okay? And now we know that it's actually an electromagnetic wave. And the way you'll see it drawn a lot, and if you're in math, what would you call that, by the way? If this is 0, it's a sine wave. Because it starts at 0, goes, that's not a very good line, is it? It starts at 0, goes up, comes down, goes up, comes down. That's a sine wave, right? That's the way we visualize what a light wave looks like. It's a sine wave. It turns out, you'll see this in your book, and I'm not going to spend a lot of time talking about it because, you know, when you take physics 4B, that's when you, like, get a lot of it. The magnetic component goes like this. It goes, if this is X, Y, and Z, it travels at a right angle all the time to the electric fields. They're always going at the same time, so electric and magnetic fields. That's the way we visualize it, okay? So here's the thing. Got this electromagnetic wave traveling through space, which I'm going to call light, okay? But if I put a charged particle here, let's make it negative since we primarily deal with electrons. That's a very large electron. An electromagnetic wave goes past it. What's that electron going to do? It's going to move, right? So when you move an electron, that constitutes what? When a charge moves, that constitutes an electric current, right? So you could have an electromagnetic wave traveling through space, and then you could have a wire, okay? And then when the electromagnetic wave goes past the wire, what's going to happen to the electrons in the wire? They're going to start to move, right? If you could measure that movement, you could record a signal that comes from that electromagnetic wave. Do you know what we call that? Radio. Like when you're listening to a radio, that's an electromagnetic wave that's generated at a tower. The electromagnetic wave goes through space, causing oscillations in the electromagnetic field. You have a wire, which is called your antenna, right? It's important that the antenna be a certain size for a lot of applications, but you have a wire that's an antenna, and it's big because you want to capture that electromagnetic wave as it passes by and get the oscillations in the electric field, and then your radio turns that into sound, right? So when we talk about, oh, light is an electromagnetic wave, we're always thinking of like Roy G. Biv, right? But in reality, it's like lots of things. It's including radio waves, and it's part of what's known as the electromagnetic spectrum. So yeah, as this wave goes past, this guy's going to move in response back and forth, and that creates, if this isn't a wire, I'm going to do this. This is not really how it works. That's your headphones? Okay. All right. That's your head. That's headphones. An electromagnetic wave causes oscillations in an electric field. It's a little more complicated than that in the way that we decode the signals and stuff like that, but that's basically how it works. Right? And then you listen to it on your radio, although I don't know if anybody, does anybody actually listen to music on a radio anymore? Car? Oh, okay, okay. Just, I don't know, because I'm pretty boring in the car. I listen to books. No, I just drive ways that I know there won't be traffic. It takes a little longer, but it's very peaceful. All right, so I like this picture. So we think of waves, light waves, as being these hang on, being like this. I think I can draw at the very top of this and have room. Oh, I'm out of space up there, okay. We think of light waves being like this. Okay. One of the early scientists to study light, and you'll notice this scientist here, he looks pretty, like, serious, right? And you know what this is? What? iPhone? Yeah, no. He's like a rock star. Look at how this woman's like, wow, that's really amazing. And this lady looks like she's actually serving a drink or something. And this is like maybe an early physicist hangout. What's that? No, it's not an Erlenmeyer philosophy. It's actually this. This is the actual one. It doesn't look quite like this, but this is a prism. This is actually a drawing of Isaac Newton. So Isaac Newton was like a rock star, right? The physicist Isaac Newton, gravitational laws, the apple. And I went to Cambridge, and they had this picture, and I'm like, well, I can't pass this picture up. It's like, hey, ladies, check this out. Right. He looks so serious in the picture, too. Not quite sure what his deal is in that picture, but anyways, he's showing this prism. I'm trying to understand the properties of light. And that's why we know that it's a wave. A lot of what Isaac Newton did helped to understand what that light was like a wave. Huh?
It looks like James McAvoy.
Don't know who that is, sorry. So, sorry. I know, I've been too busy lately. So here's light.
He was the fawn in the Chronicles of Narnia.
Sorry. Oh, is that in the book? Never mind.
Well, he was
He wasn't in the book, then I don't know who it is.
The main character in one, two.
Sorry. Princess Bride? I got that. It's even on my iPad. We can just watch it right now if we really wanted to. Okay, so light's a wave. Okay, so the characteristics of a wave, some of the characteristics of a wave are its wavelength. All you have to do to know the wavelength is measure the wave, right? How long it is from 2 points that are exactly the same. Like either tops, the bottoms, the middles, as long as it's exactly the same point on the wave. This is the wavelength. It's given the symbol lambda. And lambda is measured, like it says down in here, it's measured in meters. Okay? Of course, here's the tricky part about doing that. They're moving. Right? When you think of like water waves or sound waves, you know they move, right? Because if light waves didn't move, right, you'd never see anything. You'd be kind of like, oh, and if sound waves didn't move, you'd never hear anything, right? So we know that waves are moving, and so actually to measure the wavelength is not actually as easy as it sounds. We infer usually what the wavelength is. We actually we assume it's a certain value. Okay, so here's the other thing. Since the light waves are moving, okay, let's say they're traveling in this direction. And Isaac Newton is our observer, okay? And the light waves are coming past him. He could count, if he could actually see individual waves, he could actually count the number of waves that pass him. And if he figured out how many waves passed him per second, because remember, the light waves are traveling. If you figure out how many light waves passed him per second, that's what we call the frequency. Just waves that pass a point. And then per second. Okay? Isaac Newton being our point in this picture. Now, all light waves travel at the same velocity. What do we call that velocity?
Speed of light.
The speed of light. Okay? It's a very important number, so it gets its like special name. Okay? The speed of light is given the symbol c, and it's 3.00, roughly speaking, times 10 to the 8th meters per second. Okay, so let's think what that number is. 10 to the 6th, right? That's a million. So a million meters per second. 10 to the 7th is 10 million meters per second. So 10 to the 8th is 100 million meters per second. So light is traveling, roughly speaking, 300 million meters per second. It's like 2.99 something something. If it's in a vacuum. If there's nothing in there to interact with it, it travels at 300 million meters per second. So how fast is that? I haven't done the calculation, but that's on the order of speed it needs to be to travel around the Earth in a second. In seconds, if not a second. It's very, very fast, okay? It'd be awesome if you could drive that fast, right? Oh, I'm going to go to New York, be back in a minute, and literally be back in a minute, right? Like,
Get your jobs fast.
what's that?
You can get a job there.
Yeah, get a job, come back. I didn't get hired. I'll go to Brazil and see if I get a job there. That'd be fun. Okay, so far so good? Okay, so now Isaac Newton's sitting there. He's looking at that wave, right? And now I have a wave that looks like this. Now that one's going past him. Now, you'll notice I drew the wavelength a lot shorter, right? So wavelength is short. This is lambda for this wave. sheet. That's lambda for that wave. When Isaac Newton is looking at that wave and it's going past him, which one of those two waves, the top one or the bottom one, does he see more of per second? Top one, right? But that's only true because the speed of light is a constant. There's a lot of different kinds of waves, like waves in the water, waves, in sound. The speed isn't constant. So the wavelengths can be such that even though the wavelength is shorter, the frequency is not necessarily higher. But because the speed of light is a constant, okay?
Isn't the speed of sound constant too?
It depends on the amount of air and the density of air and all this. So yeah.
Same thing with light.
Yeah. Yeah, a little bit, but not as much so that we don't see the effect, right? But yes, speed of sound through like water is a lot faster than it is through air, that kind of stuff. Okay, so it could be that you had the situation if you had the waves frequencies were very close to each other, or the wavelengths were really close to each other, but then one was in very high density and one was in very low density. The frequencies would be not what you expect, like what you would presume they would be, because the speed's not constant. Okay. All right. So. So the general relationship, okay, is this: is that the speed of light, which we call c, is equal to the frequency times the wavelength. That is, frequency and wavelength are inversely proportional to each other. So if the frequency is really high, the wavelength is really short, and the wavelength is really long, right? The frequency is going to be really low. So they act inversely to each other. When one is high, the other is low all the time. Okay, so I'm going to draw another picture. This one's not nearly as nice as a... Okay, so now Isaac Newton, I don't know why I'm picking on Isaac Newton today. He's got his sunglasses on, and he's at the beach. Got sunglasses on, and he's got his little arms here, because he's a physicist. Wearing his Bermuda shorts. Okay, so there's Isaac Newton. He's at the beach. Probably shouldn't tell my physics friends that I do things like this. Isaac Newton's at the beach, and one wave's going like this, and one wave's going like this. Okay, so this is a nice wave like this, and this one's going up and down a lot. So he's standing in these waves, right? Which one of them is going to, push him more? That lower one, because they're the same height. I'm trying to be careful to draw them the same height. They're the same height, but the bottom one is going up and down a lot. So that's like you're standing at the beach, and the water is at your feet. Sorry, and it's coming at you all the time, right? The top one is kind of like you're standing at the beach, and your water's in the feet, and it's just going up and down and up and down. So which one of those has more energy? Bottom one carries more energy, and so it turns out one of the things to remember. As the frequency of the wave coming in goes up, the energy goes up. The more frequently the waves pass you. You think about the waves, like water waves pushing you, right? The more frequently it comes and bumps against you, the more energy it has. So wavelength and frequency are proportional to each other. Frequency and energy are proportional to each other. So as E goes up, or as frequency goes up, energy goes up. But that's the opposite of wavelength, right? So as the frequency goes up, the wavelength gets shorter. And as the frequency goes down, the wavelength gets longer. So waves that are really long have really low energy, and waves that are really short have very high energy. Okay, so we're talking about electromagnetic waves. What's short and what's long, right? It's not like you're standing at the beach and you can actually see them, which is odd because you can see light, but you can't see the waves of light. All right, so I already talked about all this. I could do that calculation later if you need me to. I'll skip it for now. So this is the electromagnetic spectrum. I like it because it's this slide because it's fairly clear. I actually don't like it because I prefer high energy to be on the right and low energy to be on the left. But that's not the way this one's drawn. Okay, so this is the kind of wavelengths that we're talking about when we talk about light. Okay, that's 10 to the minus 1 meters. What is 10 to the minus 1 meters? Yeah, it's a tenth of a meter, right? So it's 10 centimeters. So these waves, like if you could actually see them, there's a meter stick, right? Oh, that's a yardstick. It's like, that's a meter. 10 to the minus 1 meter is from this end to this end. That's how long the waves are. You can't see them because they're not like visible light, but that's how big the oscillations are, the waves when they go up and down. Okay. Frequency, though, because light is, so it's like this big, right? Because light is moving so fast, even though the tops of the waves are this long, this far apart, this is the wavelength, right? The frequency for that is somewhere around 10 to the 10th per second. So that's 10 billion waves passing you per second. Okay? That's in that spectrum and slightly larger than that in this part of the spectrum. That's actually what we call radio waves. So radio waves, what we're talking about, like when you're listening to a radio, that's part of the electromagnetic wave. It's part of what we call the electromagnetic spectrum. Then there's microwave. Like, where do you hear about microwaves? Microwave ovens, right? Microwave ovens generate the waves, electromagnetic waves, that are really well absorbed by water. And so water's in this microwave called a cavity. The microwave radiation hits the water, and just like this is absorbing all the colors other than like teal or whatever that color is, right? Water absorbs all the microwave radiation, and then what happens to your food when you put it in a microwave? It gets hot, right? What happens to a black car in Fresno? Gets really, nobody buys black cars in Fresno, I hope. But. Sorry? What do you know about a black car in Fresno?
It's a bad idea.
It's a bad idea. Why is it a bad idea? It absorbs why is it black? Because it's not reflecting any light. So all the solar energy that comes into your car gets absorbed by your car, and it gets really hot, right? That's what happens to your food. It's just a different principle, right? And you didn't know you're going to be an example in lecture today. Sorry. So, and then there's these, right? Near and far infrared. So actually, what I want you to know when you're learning this stuff is the order from of these different kinds of electromagnetic radiation in the electromagnetic spectrum. You don't need to know these numbers that are all over the place here. But let's see, where was that? Oh yeah, infrared. Like when you go to like the Carruthers Fair is open now. I think they just opened. I think that's one of the only ones. You can go to the fair for free kind of thing, but then they charge you for the stuff on the inside. But anyways, I don't remember how that works. So you go to Carruthers Fair, and you're going to buy food, which I don't know why people go to a fair to buy food, but anyways, they do. You go to the fair, and you go to buy food. Sometimes they don't cook it for you right away. Right? Sometimes it's already cooked. Where do they put it if it's already cooked? Under a heat lamp, right? Heat lamps use infrared radiation. Okay? So again, Turns out a lot of organic molecules, things containing carbon, nitrogen, oxygen, hydrogen, are really good at absorbing infrared radiation. That's actually one of the ways we analyze organic compounds is by shining infrared light through them, right? So organic compounds are really good at absorbing this stuff, right, which is what is produced by a heat lamp. All right, so visible. That's visible light. And you notice in the spectrum so far, this is 10 to the minus 1, 2, 3, 4, 5, 6, right? So these are orders of magnitude. So far, we've gone through 6 orders of magnitude, right, or more, because these longer radio waves can be meters and meters long, okay? Light, visible light, only goes from 400, well, actually about 350, to 750 nanometers. It doesn't even span an entire order of magnitude, okay? So we think about light as being everything that we see, but in fact, light is part of the electromagnetic spectrum, and it's only a small fraction of the entire electromagnetic spectrum, okay? Now, red, this is Roy, right? And this is violet. They're supposed to be violet. Roy G. Biv. It's actually spelled backwards on here. R-O-Y-G-B. I guess this is indigo. I don't really know what indigo is. And violet. So that's Roy G. Biv going this way. Okay. Long wavelength, short wavelength, right? Or shorter wavelength. So which end is the high energy side? This side. This is high energy over here. So this is the higher side. And on this diagram, this is generally true. This is the lower side. Okay. So we have the higher side over here of energy and the lower side over here. So the really lowest radio waves, and like your cell phones, right? Cell phones or cordless phones or your wireless routers in your house, those are all operating in that radio wave region. Those are all very low energy devices. And you notice we're heating food up with like actually microwave and infrared, and we can use visible light to heat it up too. Then we get to near ultraviolet, far ultraviolet. So those are the things. What's bad about ultraviolet radiation that they tell you about all the time?
High energy.
It's very high energy. What does it do to your skin? Gives you skin cancer, gives you little blobs and tumors and lesions. Why does it do that? Think about it now.
This is high energy.
It's high energy. It has enough energy to break chemical bonds. Okay? What are you? You're just a giant molecule with legs, right? And so your DNA, right? Light hits it, it can fragment your DNA, and as a result, right, get errors in your genetic material, which then get transcribed and translated and all that stuff into bad things like tumor growing cells, things that don't have growth control or inhibition to growth. Okay, so that's probably also the reason why you don't use ultraviolet like to heat your food, right? Because what are you doing when you heat your food with ultraviolet? You're going to break bonds and cause chemical modifications. Doesn't sound like a good idea, right? Okay, and then there's X-rays. X-rays, good or bad? Neither. It's a little bit of both, right? But where do you hear about X-rays all the time? Doctor's office, right? X-rays in your doctor's office. Those are the X-rays they're talking about. And at the very high end, we see this stuff in outer space all the time. These are gamma rays. The very high energy electromagnetic waves. I want to say photons all the time, but very high energy electromagnetic waves. Okay. These are the things that we see coming from processes that are related to nuclear reaction, black holes, those kinds of things. Super high energy electromagnetic waves. Just two little side notes. Insects, like we see in the visible range, right? Why is it called the visible range?
Because it's visible to us.
Because that's what we can see, right? Kind of makes sense. Insects can see outside of the visible range. So if you take an ultraviolet, a camera that can take pictures in the ultraviolet, and you go and take pictures of flowers, right? Guess what happens? There's whole different kinds of patterns on the flowers that are used as signals to the insects that pollinate them. Like little, almost look like little runways, like little stripes that go towards the center of the flower. And then at night, just another side thing, right? You're going to bed, you turn the lights off, you have the windows open because it's a really nice night in Fresno, which I don't know when that happens, but it's going to happen eventually. And then mosquito comes in, right? You know what I'm talking about? And then you get up in the middle of the night and you get a towel and you start trying to kill this mosquito. Have you guys ever do that? I don't know. I've done that so many times. How does the mosquito find you? It can see in the infrared. Okay. What is infrared? What are we talking about? That's heat, right? It can actually see heat and it can see carbon dioxide. Where's carbon dioxide come out? Out of you. Right, so the only way you can avoid this mosquito, I always tell people this at night, the only way you can avoid the mosquito is by not having a body temperature and not breathing, because
So you're dead.
yeah, that's the way the mosquito would be like, oh, that looks just like everything else. I'm going to look for something that's alive. I actually have a friend who has a fairly ingenious trap. He does mosquito genetics. He looks at the transmission of diseases across continents. And so what he does, he has to go out and capture mosquitoes, right, and then extract the ovaries. He does this by hand, by the way. So a mosquito, can you imagine how hard it is to find a mosquito ovary? Mosquitoes are small. Mosquito ovaries are smaller. You have to get under a microscope, dissect it out, you pull it out, then you do the genetics on it, right? And he looks at how the genetics of the mosquitoes move across continents. So anyways, this is for studying malaria, which is still one of the, I think the #1 killer in the world still. Yeah, we think about all these other diseases, but those are all first world problems. In the third world, it's malaria, right? So what he does, though, is he does this genetics of mosquitoes, and so he actually does a lot of stuff for the mosquito abatement. So how do you know that these bad mosquitoes are all over the Central Valley now? It's because he's doing genetics and he's identifying mosquitoes all over the Central Valley. So how do you catch mosquitoes, right? You have to trap them. So you can use live animals. Like in Africa, he'll use like live animals. You take a chicken and put it in a cage, and the mosquitoes like are everywhere. They attack the chicken. He captures mosquitoes from them. And he uses he uses the chickens to feed the mosquitoes. Oh. Anyways, takes a white styrofoam box. Okay, this is how he captures a lot of. He used to capture. I don't know if he still does. White styrofoam box. Now remember, he can't damage the DNA because that's what he's going after, right? And he drills a hole in it. Okay, what do you call a white styrofoam box, by the way? Ice chest, yeah. You go buy Save Mart, buy a $1 ice chest. You drill a hole in it and you throw dry ice in it. You can buy that at Save Mart too. Throw dry ice in it and you tape it shut and you put it outside somewhere, right, where you want to capture mosquitoes. What do the mosquitoes naturally do? They see the carbon dioxide coming from the dry ice. And this hole, right? It's like that's a simulation of your head, I guess. I don't know. Mosquito comes in. He flies into the hole because he's the CO2. And then what happens to him? He freezes. So they just fall to the bottom, and they're not damaged. You can pull them out and extract the DNA and analyze them. Okay. Yeah. It's fun stuff. Okay. I'm going to pause here. I'm going to keep lecturing. All right, let's get started again. The title of the folder that this comes out of is kind of funny. It says Bath 2014, like it sounds like it's the bath I took in 2014. But anybody know where Bath is? England. This is Bath, England. These are the Roman baths, and I led a tour, actually, a history of science tour, actually, in England and Scotland 4 years ago. No, 2 years ago now. And it was fun. We tried to get students to do the same thing in Sweden and Denmark, and it fell through. So we took a group of people to England and basically most of Great Britain. Huh? We might do it again with students in a couple years. The guy would do these things with. I got a job in San Diego. Poor guy has to live down there. It's rough. Raise a family in cool weather and nice air.
San Diego?
San Diego, yeah.
That's
So, anyways, he's down. Huh? He's down there. I'm up here, and it's really hard to coordinate these things. And so, we wanted to do some together, but schools don't. We're going to do study abroads with students. They don't usually let you have faculty from different schools lead, and actually, this kind of thing is a lot of work. And the way we do these trips is we went to Cambridge, Oxford, University College London, University of Edinburgh, Manchester University. And so when you coordinate all these trips and visit these chemistry departments and learn about the history of science and that kind of stuff, it takes a lot of phone calling and a lot of arranging of time, and really not a one-person job. And so to have both of us be at different places, just doesn't work out. But it was fun to do at least once. And so this is Bath in England. These are Roman baths. And the only reason I'm showing you this is because there's water, and we can study the properties of waves in water, i.e. this is a write-off. So, no, I actually wasn't. But this is Seth Yates. He's one of the instructors here. And you can kind of see he's flipping a coin. That's what he's doing. And the coin is going into the Roman bath. This is actually a wishing well in the bath. And you can see all these little spots. Those are all coins, all right? But what's happening here? What happened? The coin hit the water, okay? And what is it going to make? What is it making as it falls in the water? Making waves, right? And these are what we consider, this is how we conceptualize waves. They're these ripples through some sort of medium. And in this case, the medium, right, is water. And for light, it's an electromagnetic field. But in water, it's water waves. And so then what we did is we threw two coins. And this came out blurry, unfortunately, because it's pitch black in here. And we ran out of money. So I had to use the blurry pictures, okay? This is one of those horrible things where you have this great idea. You're in England, in Bath, England. All you have, do you guys know what kind of coins they have?
pens.
They have pound coins. And they've got other smaller coins, but mostly when you're traveling, you don't carry all those other coins. You have pounds. Now, a pound is, anybody know?
Like $1.20.
Yeah, when we were there, it was like $1.50, $1.60. So that's what we were throwing in. So I'm going to color code this so that it makes some sense. So the wave goes like this. And again, this is a sine wave kind of pattern, right? So if I was in a math class, let's say, which parts of the waves would be positive? Top part, assuming that 0 is in the middle, I would assume that this part's positive. And the part that's negative would be the bottom part. So that would be like this. Okay. And the reason I'm doing this color coding is it's really easy to see on 2 dimensions what's positive and what's negative. Like I have X and Y, right? Positive's up and negative's down. How do you do that in 3 dimensions? When you have a 3-dimensional object and it's a wave and it's in the positive phase of the wave, how do you show that? Because 3 dimensions is the only space that we can see, right? So we're going to have to tell whether or not a wave is positive or negative by color coding it. And blue is generally considered to be the positive part and red's considered to be the negative, okay? So if I draw something like this, and it's a sphere, like a basketball, right? And that's the wave of the sphere. What's the sign of the wave? Right, well, it's negative because I colored it as red. But if I were just drawing the wave itself, again, remember, why is the sphere significant? Because that's the way we think of how atoms look, right? If I were just drawing the sphere, it would look like that. But if I was drawing the sphere and the sign of the wave, that whether or not it's positive or negative, I'd have to put color on it in order to do that. So that's why I'm doing that. So waves can act constructively. So watch this. I'm going to cheat here. And so the two waves, if they're traveling in space, and you remember when the waves crossed each other and looked like they were going through each other? Imagine that they line up like that, okay? And they're going through space. What's going to happen here when the two waves cross, or here when the two waves cross? Well, since they're both going up, right, and both going down at the same time, they'll go twice as high and twice as low, okay? So what you end up getting, I'm going to try to do this. I don't know if I can do this or not. I don't think I can't stretch it, okay. I'm going to try, I want to try stretching this, but otherwise I have to, yeah, I'm just going to have to redraw it. The wave's going to look like this. And then what happens is the positives are twice as high and the negatives are twice as low. So this is like this. And I'm already not matching colors well, am I? Like that. Right, and you kind of know that already from math because you take sine of x and you add sine of x to it. What do you get? 2 sine x, right? It's twice as high. That's literally what you're doing, okay? And in fact, the equations that we use for describing the electron behavior in atoms is actually with like sines and cosines. Okay, so the waves, we talk about electrons, we're going to talk about them as waves inside of atoms. We describe them using sine and cosine like functions. Okay, so let me delete some of this. Or maybe I won't delete some of it. Now, I'm going to have to be a little bit careful here. Let's say they're traveling through space now, and they look not like that, but like that. Okay? So now what happens at this point here?
Zero.
You get 0 because the high and the low cancel. And so when the waves crossed in that picture of in the pond and the waves were crossing, that's why you got like parts that were flat in the middles, and you had parts that were like high and parts that were low. That came from constructive. But the flat parts come from what we know as destructive interference. So constructive creates a bigger wave. Destructive creates a smaller wave. And then there's variations that are partially constructive and destructive, but we like to think in terms of completely constructive and completely destructive. Okay, so that's how we're sort of laying this out. So what does the wave look like that comes from that?
A flat line.
When you add those together, right, you're going to get that. And so that's why in the picture sometimes it crosses, like you see the water doesn't look like it's moving anymore, okay? So if you think about this going out in a circular pattern, you can imagine how complicated the picture gets. I'll show you some of that stuff in the next lecture, how that pattern develops. I'll try to do what's called the 2-slit experiment with a piece of foil and a screen. All right. So yeah, so diffraction patterns are those patterns created by interacting light waves, but what we saw is you can get it in water. You can get it in a lot of different mediums where you see that, okay? So let me ask you, this is kind of a weird question, but it's related. How many of you like to sing in the shower? Right? And then why do you like to sing in the shower? Because you, what's that? Because you like to sing naked?
No one can hear you.
No one could hear you. Oh, yeah. I wasn't sure what you said, but that's what I thought of immediately. So, yeah, because you sound better and because nobody can hear you. So what's going on, right? So let's think about sound waves. You're inside this, we're inside the shower. It's got hard walls on it. And as you sing, the sound waves are bouncing off inside the shower, okay? If the sound waves are all begin to line up, not like this, but like it was before constructively, the sound gets bigger. Then all the stuff that doesn't fit in the shower does this. All the sound waves that don't line up perfectly begin to cancel out, and those bad sounds begin to go away. So your voice literally is better when you're taking a shower because the shower helps to modulate your voice so that you get what we call resonance going on. Your voice sounds louder.
So you don't technically have to be showering. You can just stand in the shower.
Yeah, you could literally just stand in the shower and sing. Now, there might be some truth to the clothing thing, because clothing dampens sound. You might, the water dampens the sound too, so you might need to put like, either be naked or hang towels, and I'm not sure which is going to be better. I don't want to think about it, so we'll move on from there. Okay, how does a laser work? Anybody know? If I take a laser and I shine the laser, how many colors of light, when you think about colors or frequencies of light, come out of a laser?
One.
Only one. Okay. Right. The way a laser works, okay, is at least in the old days, they make a tube, they evacuate it. There's a mirror on this end and a mirror on this end, and then there's a light source that pumps into the laser from one end. Okay, so when that light source is pumping into one end, what ends up happening is the light waves are doing this. It turns out inside the laser, in the old-fashioned lasers, there's a mirror on each end of that chamber, and the light waves bounce back and forth. And guess what happens? The stuff that doesn't fit destructively cancels, and then the stuff that fits perfectly begins to amplify, right? Begins to constructively interact and amplify and get bigger. And so laser stands for what? Light amplified, stimulated, something like that. But anyways, I can't remember the whole acronym, but laser, it's the amplification of light as it bounces back and there's constructive interference from the ends of the mirror. Now somebody's going to look it up and tell me what it means, I'm sure. Okay, so that's, anyways, I wanted to get you the idea. That's what constructive and destructive interference are, and we see them in a lot of different places. Okay, so prism. This is where we get to use the prism glasses again. Okay. Now, when you put the prism glasses on, I want you to take a look at something. I'm going to have you look at a light source. And I will miscellaneous, let's see, what do I want in here? I actually want mercury. You guys, there's glasses up here. You guys. Yeah, I'm going to turn a light off in a second here. Get my iPad back. Oh, I lost the lid for this. Great. There it is. I don't know why I left it there. I'll black this out. It's really dark now, right? And again, to remind you, I do this. What do you see? You see all the colors. It's called a rainbow, right? You see a rainbow. I'll give you the technical term for it. Okay, you see all the colors, a rainbow. This is known as black body radiation. Now, it's kind of a weird name, but you can get this kind of radiation from a lot of objects when you heat them up. So if you, for example, if you have a stove and you have how many of you have electric stoves? Anybody have an electric stove still? Yeah? You turn it on. What happens? There's an element in the electric stove. What happens to it when it gets hot? It turns the coils orange, right? But if you took a piece of metal and you heat it in a fire, you could get the same orange color, right? That's called black body radiation because normally it's not, doesn't have light. And so as it heats up, it begins to produce light. And the hotter it gets, what happens when we call it a black body, when a black body gets really hot? What colors does it produce? All right, it starts out as red, and then when you get a really hot piece of metal, it's white, right? Why is it white? Because it's producing all the colors of light. All the colors of light add up to be white. And if you actually look at it in those glasses, you'll see a complete color spectrum, okay, from the black body radiation. So that's kind of what people expected to see most of the time. And then they were able to capture gases, put them inside tubes, and then use very high voltage to excite the atoms. And this is what they saw. What do you see? Yeah, 5,000 volts tends to mess things up a little bit. What do you see? Are you seeing what? Are you seeing a rainbow anymore? No. Sorry, that flashed, didn't it? That was awesome. All right, I'm going to cheat and try to capture it on here so we can talk about it. But my you're seeing that, right? Or something similar to that. Cameras aren't very good on these devices. You're not seeing the orange and the red, for sure. I'm turning that off. I'm going to turn the light back on. So you're seeing that. And so, are you seeing a rainbow? No. Look at here, all right? You see, these are all images of the same tube, right? And you're seeing like yellow, green, and blue. You're not seeing all the colors. So it's very unlike black body radiation. Black body radiation, when you look at it, it's a rainbow. It always kind of looks the same. Turns out every element that you put in here gives you a different color spectrum. So the dilemma, the thing they didn't understand is like, where do the lines come from? Why are there lines when you heat up or you electrify elements like this, but when you heat up a piece of metal, you see a rainbow? What is it that causes lines to form? Now, remember, the color is related to the what? Frequency, the wavelength, and the energy. Okay, so I'm going to give you an equation, and I haven't done anything with this equation yet, so there really is no substantiation of the equation. I need my little pen here. Is it recording still? Yay, it's still recording. It's this. So nu is the symbol that we use for frequency. H is known as Planck's constant. It's 6.626 times 10 to the minus 34 joules times seconds. Like that. 6.626 times 10 to the minus 34 joules times seconds. So the energy of the light, this is how you calculate it. Remember we said that as the frequency goes up, the energy of the wave goes up? The actual number of joules that you can calculate for the light is given from this equation. E is equal to h nu. And h is the constant that converts frequency into energy. So if the frequency was 0, the energy would be 0. Which is kind of a weird thing to think about, how you get the frequency to be 0. What does that mean? But never mind. We'll move on from there. So, also we know that the frequency times the wavelength is equal to the speed of light. And so you can do a real quick rearrangement, because you know frequency then is c over lambda. And so what you can do is you can take that and substitute it in. And when you do that, you get hc over lambda. So the energy can be calculated two different ways, either directly from the frequency or using the wavelength in this rearranged form of the equation. Now h and c are both constants, right? H is 6.626 times 10 to the minus 34. C is the speed of light, which is 3 times 10 to the 8. Okay? Just to show you how units work out. All right. So that's H, right? C is 3.00 times 10 to the 8th meters per second, like that. And then wavelength is in meters. And since I don't have a wavelength to stick in there, I'm just writing the units. So what ends up happening is seconds will cancel here and meters will cancel here. So you end up in the end with units of joules. So you'll get some number here and then joules. Okay. So when you're seeing colors of light in the spectrum, each one of these has an associated wavelength. Okay? That wavelength is related to the energy of the light. So here's the thing that you have to recognize then. When you're seeing a rainbow, you're seeing all energies. When you're seeing a line spectrum, there's only certain energies that you see. And so then the question becomes, why are there only certain energies that you see, whereas in black body radiation you see them all? Okay? And this is the problem that they had with line spectra. They didn't have a description of it. And so this is what I'm going to do. I'm going to cheat. I'm going to give you the answer, which is related to today's lab. Okay? And then we'll do some details. So it comes down to a guy named Niels Bohr. Niels Bohr was trying to understand the structure of matter. Wow, when you're doing black on black, you really can't see what you're drawing over here. I don't even know where I am on the screen. I better make a different background. Hang on. I do like the black, but it's very hard to tell where you're at. So I'm going to kind of fake it, semi-black. So Niels Bohr, we call this the Bohr model. So Bohr model. Around 1914 is when he published his theory. So just past the 100-year anniversary of that discovery, maybe 1910. I can't remember. But it's just past the 100-year anniversary. His office is still intact, by the way. They kept his office. Now they just use it as a meeting room. So he's all these stuff around his office from when he used it as an office. So he's got pictures signed by Einstein and all these famous scientists that made great discoveries in the early 1900s. But Bohr basically said, hey, I want to explain the behavior of hydrogen. So he's looking at the hydrogen line spectrum. And his model that he uses for his to explain this is that the atom, like a hydrogen atom, so there's the nucleus, that's a plus, right, is like a planetary system. So if this is a planetary system, what am I drawing going around the sun? The nucleus is like the sun, right? These are the orbits, right? So his idea was you have these orbits, and inside these orbits you have electrons, and the electrons are moving around orbits, okay? So remember, how many electrons does hydrogen, the atom, have?
One.
Just the one, right? So it's got this one electron in this orbit. It's got a negative charge to it. Oh, you know what I'm going to do? I'm going to make it red. Shows up better anyways. And it's traveling around the sun, right? It's traveling around the nucleus. And if it's in this orbit, it can't get any closer. This is the lowest energy orbit. And he gave it designated a quantum number for it. He called it N, and he called that 1. So that's the lowest energy for the hydrogen atom electron. And this is known as the ground state. What does it mean to be in the ground state? It's like when something's on the ground. My music teacher used to always tell us. His name was Burl Walter, Mr. Walter. Still is, actually, still around. When we drop something, you know what he would always yell at us? He would yell, "Leave it, it won't fall off the ground." Like, oh yeah, hey, hey, hey. Mr. Book was the one who used that originally on that, but yeah. There was another music teacher. Yeah, leave it, it won't fall off the ground. We're like, huh? You know, high school students, junior high students. Anyways, yeah, that's the ground. Can't go any closer. That's the very lowest it could be. And it's the lowest potential energy state of the electron. Right? So it's the most stable point, if you want to think about it like that too. So now let's say you pass a strong electric field through this atom, right? What happens to the electron? Well, if the atom is going to absorb energy, right, it has to move from n equals 1 to somewhere higher into one of the higher orbits. So it goes up to here, let's say. So this would be called the n equals 1 to n equals 3 transition. Okay. If there was more energy that you put into it, right, where would it have to go? Would it go to 2? No, it would have to go further out. And these orbits go out for infinite, there are an infinite number of them, okay? Now, I'm not drawing the spacing correctly, because if I do, then you can't see anything, okay? But if you draw the spacing like I am here, well, it could go really far away, right? And that would be higher in energy. Okay, so here's the thing. That doesn't produce light. It absorbs light, or absorbs energy. It doesn't produce light. What produces the light is when the electron starts high and comes back down. Okay? So the energy of the light, so let me draw it like this now. I'm going to flatten this out. This is going to be n equals 1. Okay? And then 2, 3, 4, 5. And I intentionally drew them closer together as you go up, because they do get closer together as you go up in terms of energy. And on this axis, this is the energy, right? So right now I have an electron as n equals 3, okay? And if it's going to give up energy, right, and produce light, it has to go like this. Or it could go like this. Make sense? Either one of those will give off light. Now, will the energy of the light that comes out be the same? No, because the spacing between the orbitals is different, right? In one, you're dropping past and going all the way to the bottom. In one, you're stopping kind of halfway in between, okay? So, which one of these has higher energy? N equals 3 to 2 or N equals 3 to 1? 3 to 1, right? Higher energy means what about its frequency? Energy and frequency go together, right? So high energy means high frequency and short wavelength. That's the answer to that question, I think. Related to the answer to that question. Yeah, so N equals 3 to 2 and N equals 3 to 1. High energy, higher energy. That means, I should probably put an H in higher, huh? Higher energy and frequency, shorter wavelength. So I'm going to keep my chart. I'm going to erase what I drew on the left there, and then I'll erase what I drew on the right when you guys get caught up. Okay. So this is the thing. And the hydrogen atom, right? All the visible light comes from transitions down to 2. We don't see the transitions down to 1, right? Because they're not in the visible region. They're there. There's a lot of them. We don't see them, okay? Those are actually in the ultraviolet. Because remember, ultraviolet is higher in energy. So transitions from like 2 to 1 and 3 to 1 and 4 to 1 and 5 to 1, those are all ultraviolet radiation. You can't see them. The ones that are in the visible range are from, for example, 5, oops, I mean to erase, 5 to 2, 4 to 2, and 3 to 2. Okay, which one of those is the highest energy? 5 to 2. Which one do you think is red? 3 to 2, because red is the lowest energy that you see, so 3 to 2 is going to be red. 5 to 2 will be purple or violet. Okay? We're seeing energies with our eyes, but we don't know that those are the energies. Like intuitively, we just see colors. Okay? So here's the thing. Bohr's model of the atom made it really simple. There's this constant, it's called RH. Now, I don't like the version of RH and the version that your lab gives. The one I like is 2.18, I think it's 2, times 10 to the minus 18 joules. It's 2.18. I can't remember if it's 2 or 1, because you have to round it. It's I don't remember if it started out as 0 or 1 at that point. Okay, so that's telling us about the spacing. Actually, it's related to the spacing and energy in joule units of these values here. Okay? And what Bohr said is the energy of any given level, E, is equal to the negative of RH over N squared. So RH is 2.82 2.182 times 10 to the minus 18 joules. And if you want to know the energy of any one of these levels, okay, you just have to divide by the quantum number n and square it. So, okay, so why does this make sense, right? Think about this. Why does this make sense? Remember we said this is the lowest in energy, most stable, right? So it has to be the lowest value. The lowest value, if you put 1 in here, that's negative RH, right? So here, I'm going to actually, again, I'm going to erase a little bit. This value at the very bottom, if you were to plug into this equation, you stick a 1 in here. So that's just minus RH. What if it's 2? Like, what is the energy of this level here? Well, it's minus RH over 4. Which one of those is going to be lower in energy? Right? Is this one down here? Because this is 1/4 of this value. But remember, this has a negative in front of it. Right? So these are lower than these ones are because of the negative sign. And as this number gets bigger, this is going to be divided by 9, divided by 16, divided by 25. What if you went to the infinitieth level? I don't know if you can do that, but let's say you went to the infinitieth level, right? What's E equal to? Well, it's minus RH over, and I used to love this when I was a kid. Infinity. Infinity squared, right? What is that? No? It's like a number that's really small divided by a number that's really big, squared. Infinity, right? That's a lot when you're a kid. 0. It's like, what is your financial value versus Bill Gates? 0. I have nothing in terms of money on him, right? This comes out to be 0. So, in fact, in the infinitieth level, that's way up here, right? That's 0. And so these are all energies lower than 0. That's why minus RH is the lowest, and so forth as you go up. Okay? So this is the lowest energy level. It represents the orbital that's closest. The infinitieth level is kind of just conceptual. By the time you get there, you leave. You're away from the nucleus. Okay? All right, so how do you use this information? Let me explain to you in the lab what you're doing. So in the lab, you're going to take a spectroscope. And the spectroscopes you're going to use are not these little cheapy handheld ones. I have more stationary tabletop versions, okay? But for all practical purposes, the heck is that? Replica grading. Holy cow. Oh, they're there. I'm going to do this experiment with you and see if it works. It may or may not work with you guys. Just look through here and look at the light up there. So what you're going to do is you're going to see numbers from 4 to, I don't know, 7.5. Okay? Right, you see the line spectrum that you see when you see the lights up here? Okay? I don't know if you can do it with this. I'm going to try it. But what colors do you see very distinctly? Red, orange, green, teal, purple, right? So I'm going to do this. I'm going to turn this light off. And I'm going to turn this on and see if you guys can see what you see. I don't know if you'll be able to do it from back there. I've got too many things on my hands here. Can you see that through the spectroscope? You're going to have to really work at it. right? Do you see the orange and green, and there's a little bit of red? You notice those are exactly the same colors you're seeing in the lights, right? What light? Do you know what? Do you remember what element that is? It's mercury. When you look at the fluorescent lights, why do you see mercury? Because the fluorescent light bulbs have mercury in them. That's how they get them to ignite and make that bright white light. There's a plasma, what they call plasma up in there. And the way they get it started is using mercury vapor. That's what that is. That's a mercury vapor lamp. So you're seeing like some of the same. Okay. So what you're going to do actually is you're going to look at hydrogen, okay? And it's going to be like 700, 800, oh, sorry, not 800. We'll start with 300. 300, 400, 500, 600, like that. It'll be numbers going across like that. And you're going to get a line spectrum, okay? What do those lines come from again? They come from the electron in the atom as they go from high energy to low energy, okay? So you're going to convert whatever wavelength you get over to here, you're going to convert that into energy. So you'll get a wavelength, let's say the wavelength around 300, because I don't have a better description of what it is yet, because you haven't measured it yet, okay? And you're going to say E is equal to HC, oops, over lambda, like that. So you plug those numbers in like I did earlier, showed you to plug them in, you get the energy, okay? Here's the thing. This is going to look a lot like the last chapter. The energy of the photon, the light wave, so I'm going to say energy of the light wave, so I'll use lambda, okay, plus the energy of the electron. Conservation of energy says it's equal to 0. Now, this part you're going to get from here. Your job is to figure out what the Rydberg's constant, the RH, is. So remember, this is the energy of the electron. And the energy of the electron depends on where it starts and where it finishes. Okay, so if it's for example, the red band, the red light, okay, it's going to be from 3 to 2. If it's for the purple one, it's 5 to 2. So this is actually the energy of 5 to 2. So what's the final state if you're going from 5 to 2? It's 2, and the initial state is 5, okay? And they tell you this. If you look right in the calculations section, they tell you, like, this is the transition for the different colored lines. So they actually tell you what it is. So it's going to be E2 minus E5. Right? Final minus initial. And that's going to be equal to, well, how do you calculate E2? Well, it's minus RH over 2 squared. And then E5, you're going to subtract that, so it's going to be minus RH over 5 squared. Okay? So that is that part. Your job is to experimentally determine RH. So you have this energy just from the wavelength. You have everything in this equation. I don't know why it's doing that, by the way. You have everything in this equation, right? For that, except for RH, right? and that's equal to 0. So since RH is the only thing you don't have, you can solve this equation for RH and calculate what its value should be. And you'll compare it to the value that I wrote earlier on the earlier slide, the 2.182 times 10 to the minus 18. You'll compare it to that, okay? That's how you're going to determine percent error. Okay, there's actually one other component to this, and I'll have to explain this to you, and I'm going to show you how to do it on the computer. I was really tired from holding that silly iPad. And it needs a spreadsheet.
Oh, yeah.
I'm actually show you how to do the spreadsheet. I decided this may be the best way to do this. What do I need to do first? I need to do that. Okay. And bring this over like that. There's a part of the spectroscope that you're going to have to calibrate. It says the very first thing that you have to do. You're going to do that with a mercury lamp. We only have 2 of them, but you don't have to do it first. You can do it second. So I'm going to be having you work in groups of 4 or so and doing this experiment, because there's a lot of holding of things that you have to do in order to get it to go off right. And I'll show you some. We'll take a break and I'll set one up for you, show you how to do it. Okay, so these are the known wavelengths for mercury. How do we know them? These are the emission lines for mercury. How do you know them? They're measured very precisely, and you know them because we gave them to you. They're actually in the introductory. It almost looks like a picture you're supposed to look at and not care about, but we give you these values in that picture. You don't know the measured values yet, okay? But what you need to know is you need to know these measured values. Now I'm going to cheat. I already have measured values in here. I'm going to get rid of the chart, though. Make this go full screen. Like that, okay? So these are now, I did the experiment while you weren't looking. Right. Those are my measured values. You notice they're not the same, right? These are actually somebody else's measured values. The reason they're not the same is because the way you look through the spectroscope determines where you see the different lines at. And so what you have to do is you have to calibrate the spectroscope so that when you read it, that you can determine what the known values are. Okay, so what you're reading isn't the known values, but you can use, you can calibrate the instrument so that it relates to the known values. So these are the known values. This is what somebody measured. You notice they're all off by a little bit, right? So what I'm going to do is I'm going to make a graph. And I'm going to go like this. I'm going to insert a graph. And I chose a scatter plot. A scatter plot is XY graph. That's a scientific graph, okay? And I don't like the scaling, so I'm actually going to change that. Let's see if it's going to be nice or not. Axis options. I don't want it to start at 0 because I can't see much on my graph. So I'm going to start it at 350. And then I'm going to start this one at 350 as well. And the reason I'm choosing 350 is it's slightly smaller than my lowest value. Okay, like that. So those are the data points. And then what the procedure tells you to do is to put a regression line onto the data. A regression line is what we call the best fit line. Right, so I'm going to just right-click the data point, and I'm going to add a trend line. If I double-click on that trend line, I get to set options, and they tell you to display the equation on the chart and display R squared. So there's your equation and your R square value. I don't like the font. I want it to be bigger than that because I'm getting old and blind, so I'm going to make it big like that. So what did I do? I made these the x values. These are x values here. These were the y values here. That's what's graphed over here. This is y, this is x, okay? Now, this is for mercury. But it's the calibration graph for all the data that you're going to collect in the lab. So let's say your hydrogen line, let's say it comes out to be 300, okay? That's on this axis. Well, actually, this make it one. Let's make it 500. Okay, so let's say you have a hydrogen line, and this is its wavelength, 500 nanometers. Okay. Where is that here? It's right here. What value would that be on the x-axis? This is the corrected value down here. It's corrected because you use this line, right, to determine what its value is when it's corrected. That is when you take into account the calibration of the spectroscope. Mathematically, what you're going to have to do is you're going to have to take your equation, and for y, plug in 500, and for x, you'll solve the equation to get what this value is precisely down here. Okay? Now, graphing takes a long time. Every group of 4 of you has, well, it doesn't take a long time if you have a computer and a printer and all that stuff, but how many of you brought a computer and a printer?